So how would you describe the world of warfare? I mean, if I try to describe a system, we have different parameters. We need to talk about domains, dimensions, rulers and protractors, or sensors, players, laws. So what are all these aspects? I mean, how do you accurately model this world? What do you need to take into account to make some good model of the world of warfare?
So let me pull two threads here. The first one is sort of I'll say a bounding framework for what you described. There's something that's a sort of a driving trend right now within the U.S. DoD. It's got a couple of different names, but for purpose of this discussion, we'll use one of the names that goes under Joint All-Domain Operations or Joint All-Domain Command and Control. So we'll just call it JADO. And the key thing there is all domain. Let's talk a little bit about what a domain is. Historically, you got an army that fights on the land. You got an air force that fights in the air. You got a navy that fights at sea. So we talk about those physical domains. There's been a lot of press over the past year. We just passed the first anniversary of the U.S. Space Force. That's an acknowledgement that space is a domain. People talk a lot about cyber or the electromagnetic spectrum. Those are all domains. I've even heard of a domain referenced before when we start talking about things like information or, I'll call it the cognitive domain.
Yeah.
People refer to hybrid warfare or gray zone warfare, hearts and minds, things of that nature. So all of those are different domains. And one of the big trends right now is a realization that you really put yourself at a disadvantage if you look at only one domain, or even you look at multiple domains, but each individually. Because the reality is all of it's very, very interdependent and codependent. The second big factor that ends up popping up, and they're both directly connected, and the punchline here, I want to come back to the question of complexity and dimensionality in all of this. The other one is speed.
Yeah, time.
Yep, time. And one of the terms that we've been starting to use around DARPA, in fact, I'll give credit to our director for inspiring this term, Victoria Coleman. We're calling it time compression. It's how can we make time speed up, essentially. How can we, at simplistic level, it's how can we do things faster? But there is this traditional determinism, particularly within DoD, that likes to say, okay, I want to study things and try to forecast, what the future is going to be. And in the process of doing that forecasting, come up with every possible contingency. And then I'm going to go build one, heck of a powerful system that is either, has a high enough performance level or is adaptable enough that it's going to address every single one of those contingencies. The reality is we are now in such a complex, multidimensional world that I'll posit that this forecast model doesn't carry. So instead, we have to be in a mode of rapid responsiveness. How can I just sort of assume that I can't, how can I acknowledge, not just assume, how can I acknowledge that I can't predict the future, with any degree of accuracy? And there are going to be contingencies that occur that I just haven't forecasted. So how can I be in a rapid responsive mode? That's time compression. And so a lot of what we're looking at right now is both of those big themes pulled together. How can we be all domain and recognize all the interdependencies of this very high dimensionality space? And how at the same time can we do it with incredible speed in this notion of time compression? There's an interesting little aside, if I can. I love this story because it shines a light on this issue of time compression, and it's about toilet paper of all things.
Okay.
This was inspired by an article I read in Fortune magazine back early in the pandemic.
Yeah.
And they were talking about the shock to the supply chain for consumer goods when everyone had the run on stores. And the shortage of toilet paper. And they said, look, if you look in the business world, particularly in manufacturing, they're also a very forecast-centric type of world. They do a great job at data analytics. A company that makes things will forecast out almost, to I don't know how many decimal places what they think their sales are going to be. And it's all about managing that inventory. It's efficiency. And one of the things they said in this article is that one of the reasons the shelves ended up empty of toilet paper is they were already running at something like 93% capacity, just so they were making sure they had no inefficiencies. That's great from an efficiency and effectiveness standpoint, but it leaves no resilience. That's a very brittle system. And when all of a sudden there's this contingency disruption of a pandemic and people doing a run on stores, it doesn't have the latitude to respond to that. And you think, okay, I'll take a legacy forecast approach, and it says, well, I need to open up my air bars. I need to account for, well, that's not practical, because that would say, okay, I need to have 3 times the quantity of milling machines. Well, if the typical toilet paper manufacturer, went and bought, 3 milling machines for every one they have today, they'd go out of business.
Yeah.
They can't afford that level of over-provisioning. So the answer is, what are things I can do that can be rapidly adapted? How can I measure disruption? And then what are the knobs I can turn to get to good enough? It's not going to be optimal, but how can I get to good enough in a rapidly responsive manner? And that's what I see as the big trend going forward, and that's certainly where my organization has been focused.
I think the problem with the toilet paper was that toilet paper takes space. So when people buy, let's say, 5 or 6 packs of it, they just then the next customer will see an empty shelf. So they will think they're running out of toilet paper. So you could think about compressing it even more so that it looks small, and you can put more and more so that it doesn't.
You hit the nail on the head. In fact, in this article, they talk about that.
Okay.
And that's exactly what one of these, I'll say, soft knobs is. They couldn't go whip up a new milling machine in a day. But what they could do is reprogram their production line so that they could start packaging, packages, smaller packages, fewer rolls.
Vacuum pack the toilet paper. Right?
Well, yeah, in this case, it was just doing 4 roll packs as opposed to 24. But it's the same idea, yeah.
Yeah.
And there were other things too, like, if some of the shortages were caused by disruptions of the supply chain.
Yeah.
And so, can I have what amounts to a vendor, radar for new sources of pulp and a new process for vetting and validating those providers in a faster manner? So it's a great example of taking a very system architecture level thinking of these complex problems as opposed to the obvious solution, which is build more milling machines.
Yeah.
It might be the obvious solution, but it's not a very effective one in the long run.
I mean, I was reading about, AlphaGo and all these AI systems where they take into account like certain games and so on, and then they try to build these super expert systems that can fight against or play against humans. But when you model a game, for example, chess, the sort of game tree complexity is 10 to the 120, or if it's Go, it's 10 to the 700. But when I think about a war game, that must be like thousands of orders of magnitude more complex than chess and Go. So that's why I was thinking, what are the approaches to achieve an acceptable level of modeling without something that works, but that is not too much complex? Because in theory, if you want to model things, you could start from the wave function and the Schrödinger equation. That's the most ridiculous thing that someone can do. But so what's the sort of modeling that you guys do, if I can ask this question?
Yeah, no, that's a great question, and something I personally think a lot about. And I'll even toss it out to your viewers if anyone has any ideas on how to do this kind of framework analysis in a quantitative way. I'd be interested in hearing your ideas, and who knows, maybe we'll get a project out of it. The fundamental way we're looking at it is managing. In some ways, this is borrowed straight out of network theory. It's looking at how do we manage complexity and dimensionality by breaking things apart into scale. And so, if we think about some of the dimensions you mentioned, I mean, those are consistent with some of the things we see at the decision support level inside an individual platform or a payload. And one of the things I think we'll probably end up talking a little bit more about is our alpha dogfight. But if we have a AI flying an aircraft, or we have an AI controlling a sensor payload, those kinds of decision processes are on the order of, you're saying, maybe 10 to the 200th or so. Now imagine, that platform or that payload is part of one mission unit. And that in turn is part of, whole squadrons or forces. And then I'm talking all domain and all these other types of things. So each of those is taking about that same dimensionality and now growing that geometrically. So people who think that they can take that kind of endeavor and, as one of my bosses likes to say, sprinkle some AI pixie dust on it, and just assume that some algorithmic approach is going to discover a way to manage that level of dimensionality is just really not practical. So instead we say, how can we break up those decision layers? And I'll think of it in terms of decisions that have to be made. How can we partition those into a manageable degree of complexity or a manageable dimensionality, and then still create optionality by being able to abstract those interfaces and those boundaries? So it's really about partitioning and abstraction. And if you look about it, the original inspiration for this, this was before my time as office director, but a number of years ago, maybe 2015, I want to say, 2016, DARPA sponsored a conference called Wait What? And one of the speakers there was a chaired professor from UC Berkeley. And he was one of the creators of the original design tools for semiconductors. And he really presented this notion better than anyone I've ever seen. Because it's intrinsic. You mentioned knowing the wave function. Well, at one level, if you want to do a really good semiconductor, it would be great to know the wave function of every, gate, and sink in a semiconductor. But, like you said, not practical.
Do you need that? No, probably not.
Yeah, that's right. So we've got Moore's law because of this notion of being able to manage scale by partitioning and abstraction. And then once you've abstracted things, being able to do composition with those abstracted elements. And that's how we're approaching this all-domain, warfare challenge. I will say that we're living right now in a very challenging but also interesting intersection between technology and culture. Because to live with that model of abstraction and composition drives a certain amount of acceptance of uncertainty. I don't know what's happening underneath the hood, underneath the abstracted boundary of that next module. But trust me, it's going to satisfy some function. Well, usually if you're talking to people in the military, they don't like an answer that just says, trust me. They want determinism. They want a certain number of decimal places of certitude. But I argue that is committing the Statistics 101 fallacy of mistaking precision for accuracy. We're living in such a complex, dynamic world that we have to be able to back to the toilet paper, live with disruption, live with uncertainty. And the only way you do that is by, taking a more stochastic kind of model toward things.
Thank you for listening to this conversation with Dr. Timothy Grayson. And I also like to thank DARPA's communication team for making this possible. If you enjoyed this video, please leave a comment below, like, subscribe, turn on the notification bell, and support this channel on Patreon. This podcast will be also available on Spotify and Apple Podcasts, and you can find the links in the description below. Thanks for watching.